Hi, welcome along. Another video podcast. This one on circular motion, get us kicked off further mechanics in the second year. Going to try and in this one mainly focus on actually what's happening in circular motion, why circular motion is a sort of special thing to study, and really getting our head around what's going on in terms of forces and acceleration prior to getting stuck in with the maths. Okay, we're going to have a look at some examples of circular motion. I think you can know what's coming here. Yeah, something fairly extreme going on there. Just going to cycle through, if that's not too much of a pun. Yeah, definitely something quite extreme going on there. I don't think chatting about it's going to help at this point. This one's even got a car. So how does a car drive on a vertical wall? And they're going at constant speed, aren't they? So why do they need a force to make them move? Just follow this plane, level flight, wings level, and then as it goes here, that it's almost turned horizontal. Okay. So what we need to understand and this is a fairly extreme example, but it's kind of illustrates the point, the direction of the forces quite clearly. Like this one, it's just a kind of friendly, everyday kind of scene. And we're going to finish on this one. It's quite everyday and pedestrian, isn't it? But we can see there, just in this bit of everyday footage, simple examples of circular motion, and that really kind of affect our lives. Hi, so we're going to continue thinking about circular motion. We really need a toy train. I think I already drew this for you last year. So we're going around the track. I haven't got a toy train, I've got a dice. Let's just imagine it's going around. Choo choo. So it's going around the track. And let's imagine that it's going along. It's a child's toy. It's moving with a constant, I don't know, 0.5 meters per second as it proceeds around the constant. So it's got a constant speed wherever we put it. It covers 0.5 meters of the track every second. However, the vital question is, and I think we know the answer from what we've seen in the video, but let's just make sure we all get there at the same time. Is it accelerating? Well, it kind of feels like the answer is no, because the word acceleration in everyday speak, as opposed to in physics speak, means speeding up or possibly slowing down. But of course, what we know is that acceleration is rate of change of velocity. And if we think back to the beginning of the course, we were adamant that the difference between velocity and speed was direction. And clearly, the direction of the train here and the direction of the train here are different. So the velocity has changed. Not the amount of velocity, but the direction of the velocity. And therefore, there is an acceleration. In fact, you can see between here and here, there's been a change of velocity of 1 meter per second, because it's going 0.5 in that direction. A change of velocity to 0.5 in that direction is a 1 meter per second change in velocity. So we need to understand that when an object goes round a corner, it doesn't have to do a complete circle, just like the cars on the roundabout at the end of the video. It just needs to deviate from the straight ahead. And as soon as it does that, its velocity is changing and it's accelerating. Just going to try and draw a little vector diagram to try and illustrate that. So here's a section of a curved path, and the velocity at any point is a tangent, isn't it? Like that. These are meant to be arrows. And that represents the velocity after some time, and that represents the velocity before some time. So if I redraw this vector next to that vector, it's fairly clear that the two vectors are different, aren't they? So how would we make that pinky vector into that black vector? We would have to add that much. So what we've done is we've added that much to that vector to make that vector. And that vector we've added is in the direction of the centre of the circle. So that's the second fact. When something's moving in circular motion, it's accelerating. The direction of the acceleration is towards the centre of the circle. So all objects in circular motion accelerate towards the centre of the circle. You will see this diagram in books used to derive the equations for circular motion. We don't need to know those derivations, but it is useful to kind of be able to visualise what's going on. So we've had a bit of a chat about the acceleration of an object. But we know, don't we, that F equals ma. We know from Newton's laws that if ever an object is accelerating, there must be a force. So let's just try and go through all the examples in the video and make sure we establish in each case which force is responsible for the acceleration towards the centre of the circle. So first of all, you saw a loop-the-loop roller coaster. Somewhere like this, the force towards the centre of the circle will be the reaction force between the wheels of the roller coaster and the track. When it was upside down, there will be some reaction force, but also the weight, the gravity pulling it down, will also act as a centripetal force. We looked at the wall of death. And again, if I try and draw a not very good head-on view, it's the reaction force of the wall acting on the motorbike towards the centre of the circle that keeps it in circular motion. So we've got two reaction forces, a bit of weight. What about the child being swung round on Dad's arms like that? Well, that's the tension in their arms, which is the force acting, pulling the child towards the centre of the circle. I think we're going to do this a bit more in another video. Well, really not drawn a very good plane. That's meant to be a plane coming towards. It's the horizontal component of the lift force. I think I do that in a later video a bit better. Then finally, and last but not least, it's the most everyday example, we had cars going round a roundabout, didn't we? So if this car is simply making this turn like that, then it is the friction between the tyres and the wheels that's acting towards the centre of the circle. And you can kind of do a thought experiment. Let's imagine it's a frosty morning and this hatched area here is an area of ice and therefore no friction. So let's imagine that a car is travelling round the roundabout like this. The friction is acting towards the centre of the circle. It's moving in a curve. There's the centre of the circle. What happens when it hits this area of black ice? I'm just going to make my area of black ice. It's called black ice just because you can't see it. It's black on the road. Well, if there's no side force, then suddenly it carries on straight, doesn't it? Yeah? Because the acceleration has gone. There's no acceleration. You have constant velocity and you move in a straight line, and that's why you might hit the curb or a tree or something over here if there's insufficient or no friction when you're moving in a corner. You might also query, you might say, John, when I'm in a car going round a corner, there's you, like that, I do feel a force, but I would have said I feel a force outward. And that's called a fictitious force, and we need to, and if we were in a drone above you, we could understand this much better. You, as an individual, like any other objects in the universe, want to go in a straight line. the car is accelerating that way, and you'll end up leaning on the door or something. You'll end up carrying on in that straight line until you reach the door or the edge of the seat, and then it can provide a force towards the centre of the circle. So it's just a matter of perspective on that one.